Hello, and welcome to Chapter 3, where we're going to look at compounds taking elements and coming together, forming bonds, and specifically we're going to look at ionic bonds in this chapter. And then in Chapter 4, we'll look at covalent bonds. So here, of course, are your learning outcomes, what you expect to be able to do and to understand at the end of this chapter. But before we can actually dive into the bonding that's happening between these atoms, we have to understand a little bit about why they are bonding. And this has to do with something called the octet rule. And the octet rule essentially states that atoms will do whatever it takes to get to 8 valence electrons. So that means that they'll gain, they'll lose, or they'll share some electrons. So we learned back in Chapter 2 that in an electron configuration, we know that S has 2 electrons and the p orbital has 6 electrons. So 2 plus 6 gives us our 8 electrons. And remember, valence electrons are electrons that are in the outside, okay? They're in the outermost shell, or the energy level that's the highest. So we can show electrons or represent electrons using dots. So since we're talking about 8 dots, and we know that electrons fill each orbital with 2 electrons maximum, we can kind of think of it as a box and then put our dots 2 on each side, and that gives us our 8 valence electrons. So let's talk a little bit about how we can even find the valence electrons for any given element. And that goes to the periodic table. So I'm going to go ahead and pull up a blank screen, and I'm going to draw my handy dandy periodic table. So we know it looks a little something like this, right? Obviously this is not drawn to scale, but you should hopefully be able to follow along. And so the great thing about finding the number of valence electrons is that we can very easily find the number of valence electrons by just looking at the column that our that our element is in. So the column number tells us the number of valence electrons. So over here, we learned about our periodic table in Chapter 2. We have column 1A, which is our alkali metals, and then 2A are the alkaline earth metals. So those are the column numbers. So the valence electron numbers, I'm going to represent in purple. That means we have 1 valence electron in 1A. We have 2 valence electrons in 2A. We're going to skip over the transition metals because the transition metals are a little crazy, and we'll see why a little bit in this chapter. So then we can move over, and we have the column that starts with boron, right? This is 3A. Column that starts with carbon is 4A. Nitrogen is 5A. Might run out of room. O is 6A. F is 7A. And then we have helium and neon in 8A, right? So again, all we need to do is look at the column number to determine the number of valence electrons. So this 3A has 3 valence electrons, 4 valence electrons, 5, etc., all the way down the line. So we can ignore the transition metals, and we can ignore the rare earth metals down here at the bottom. Just forget about them. And another way, if you don't want to remember our valence electrons using this method, you can look at the electron configuration to determine it as well. So if we were looking at boron, for instance, which is B, boron has its 1s1, s2, and then we have one p orbital taken up, right? So we have two s's and one p. 2 plus 1 equals 3. 3 is our number of valence electrons. So we can find our number of valence electrons either way. The easiest way, in my opinion, is just to count what column we're looking at. So let's go back to our PowerPoint. And let's take a look at these examples. So we have potassium, silicon, oxygen, and magnesium. So our first step is to see what column these elements fall into. So look for K on your periodic table. Again, this is potassium. And you should see that K has a valence electron number of 1. So we're just going to draw one dot. And it doesn't matter which side you decide to draw it on. Any of the 4 sides of that box that we talked about is fine. And so this tells us a little bit about what is going to happen to potassium in order to achieve an octet. Would it be easier for potassium to gain 7 more electrons, or would it be easier for it to lose 1 electron and then go down to the next valence shell? So in the case of potassium, it's going to be a lot easier to lose 1 than to gain 7. So we'll see that potassium likes to lose 1 electron. And we'll see what that means for us a little bit later. Silicon, we go to our periodic table and we see that it has 4 valence electrons. Right? It's in the same column as carbon. It's in group 4A. So we're going to add our 4 electrons. Now, when we're adding our electrons, we do want to follow along with this idea of filling in our orbitals. So remember, we always fill in the s orbital before we move on to the p orbital. So we're going to put 2 dots together to fill in our s orbital. And then we're going to put 1 electron in each p orbital before we go back and double those up. So here's our 4 electrons, where 2 of them are paired together, 2 of them are not. So here we can ask, well, is it easier to gain 4 electrons or to lose 4 electrons? Well, it's pretty similar. So we can expect for silicon to either gain 4 electrons or lose 4 electrons. When we move over to oxygen, find oxygen on your periodic table, and you'll see that oxygen has 6 valence electrons. So we're going to fill in our dots the same way. So fill in our s orbital, and then fill in our p. So we have 1, 2, 3, 4, 5. Now we can go ahead and fill in another spot. So we're going to always put 2 together first, and then for the remaining, we're going to put 1 on each side and then double up. So this is our 6 electrons. So would it be easier to gain 2 electrons or to lose 6 electrons? Well, in this case, it's going to be easier to gain 2 electrons. And we're going to see that this very closely coincides with the types of bonds that these elements are going to make. Oxygen is missing 2 electrons, so it's likely to make 2 bonds because those bonds will contain 2 electrons. Then we look at magnesium, find it on the periodic table. We see magnesium has valence of 2. And so remember, we want to keep the 2 electrons in the s orbital together. So we just keep them on one side. So is it easier to gain 6 or to lose 2? It's going to be easier to lose 2 electrons. So now that we understand a little bit about how many electrons are involved in bonding or can be involved in bonding based on the valence electrons, we can actually start breaking this down into ions. And so there are 2 types of ions that we can generalize, and that's the anion. Anions are negative. Anything negatively charged is an anion. Cations are positively charged. So anytime that you see an ion, it's going to have a charge in the upper right-hand corner. So it might have a positive sign, might have a 2 negative sign. That means whether it's an anion or a cation, depending on if it's positive or negative. Now the fact that anions are negative comes from the fact that they are gaining electrons. Because remember, electrons are negatively charged. So if we're taking in more negative charges, we're going to become negative. Cations are positively charged because they are losing electrons. So if we're getting rid of that negative charge, we're becoming more positive. Let's talk really quick about how to find the number of electrons in an atom. So let's say that we are looking at the element C13. And it just looks like this. Well, remember that the upper right, sorry, that's the left. The upper left is our mass. And the masses are protons plus our neutrons. In the lower left, which will sometimes be written, but most of the time will not be, this is our atomic number. And the atomic number, remember, is our number of protons. And we get that number directly from the periodic table. So that's why it's normally not going to be written for you. And then the upper right is your charge. And so that charge helps us figure out how many electrons there are in that atom, because if we have a negative charge, we know that we added more electrons. If we have a positive charge, we know that we subtracted some electrons. So in the case here of this carbon 13 that I drew out, there is no charge. I did not write anything in the upper right-hand corner. So if there is no charge, that means that the number of protons and the number of electrons have to be equal. Because in order for something to be neutral, our positives and our negatives have to cancel each other out. So in this case, we would look up carbon on the periodic table to find its atomic number. We see that the atomic number of carbon is 6. So the number of electrons in carbon has to be 6 as well. Now let's look at what happens if we have a charge though. So let's say we have nitrogen. Let's say we have N14, 3 negative. Well, here we do have a charge, right? So if we have a charge, you want to start off by figuring out how many electrons would there be if this element was neutral. So if neutral, we would say that protons equals electrons, which in this case would be 7. But we know that this is not neutral. So here we can see it has a negative charge, so this is an anion, right? So if it's an anion, we are gaining electrons. How many electrons are we gaining? We're gaining 3. So an anion means we're told that we're gaining 3 electrons for this particular atom. So if we're gaining, that means we're adding, right? 7 plus 3, we have 10 electrons in this ion. So it would be the opposite for a cation. Find out how many electrons there would be if it was neutral. And then since it's a cation, we know that we're losing electrons. So we would subtract however many electrons are listed in the charge. Okay, so now you should know from chapter 2 how to find the number of protons, how to find the number of neutrons, and now the number of electrons in any given atom or ion. So now that we broke it down into the most general state, the anion and the cation, we can get a little bit more specific with our types of ions. And so our first one here is called a monatomic ion. A monatomic ion is exactly what it sounds like. Mono means one, and then atomic. So these are ions made of one atom. Okay, not even necessarily one element, one atom. There's only one atom in the entire thing. And so when we are naming these ions, we can break it down into rules based on the cation or an anion. So if we're looking at a cation, these are very easy for us to name. The cation is always going to have the same name as its element. And then we add the word cation at the end. Now I want you to note that all cations, all monatomic cations, are metals. This is always going to be the case. So I'm going to just change this element specifically to the name of the metal. Okay, so for example, we could have something like sodium. Sodium looks like this when it's in the ionic form, sodium plus 1. And so since it's a metal, we just call it sodium cation. It's that easy. For anions, it's a little bit different. For anions, you want to keep the first syllable of the element. And then change the ending of the name of the element to end in IDE or IDE. So we looked at nitrogen up above, N3-. So we keep the first syllable, which is nite, right? And then add on the ide. So this is called nitride. And sometimes you'll see the word anion added on. Sometimes you'll just see it as the nitride ion. So since we saw cations are always metals, anions are always nonmetals. This will always be the case. I do want you to note, though, hydrogen is the exception to the rule. We know that there's always exceptions in this class. Hydrogen can be either a positive one or a negative one. Okay, most of the time we're going to see hydrogen as a positive one. But I just want you to be aware it could be either way. So how do we know what the charge will be of these monatomic ions? Well, again, we can go to our periodic table in order to determine this, which makes things very nice and easy for us. So hopefully you have a periodic table with you that you can take notes on. Let's draw my fabulous periodic table again. Make it a little bit bigger this time. Okay, so again, we know that for group 1A, we have our alkali metals. 2A, we have our alkaline earth metals. And since these are metals, we know that they are going to be cations. So anything in that first column is going to have a +1 charge. Anything in the second column is going to be a +2 charge. So once again, it's really easy. We know it's a metal, so it's going to be a positive. And then we look at the number of them, and that's its charge. So +1, +2. Again, we're going to ignore the transition metals because they're weird, and we'll get there in the next slide. But they're weird because they can have many different charges. So we can't just look directly at the periodic table to figure out what their charge is. So we're going to skip over that. And then you should notice that when we talked about the periodic table in chapter 2, we kind of created that step ladder, right? Something like this, starting with boron and aluminum here. And so in the case of the metals in this column, since this is column 3A, right, everything from aluminum down is a metal, along with these guys being metals. So these are going to be +3 because it mostly contains metals. Then we get to the next column, the column with carbon. And here, we don't really even pay attention to the charges because you can see we have some metals, some nonmetals, so we end up with both positive and negative charges here. So we are going to ignore this column. The way we talk about it is this column is our switch. Because so far everything we've done is positive, and then we get to carbon and we're going to switch our sign. So now our next column has nitrogen in it, and it is going to have mostly nonmetals. So this is column 5A, and its charge, since we switched, is now a -3. Then we have oxygen, group 6A. Everything in there is going to be a -2. So now we're just working our way back down these numbers. So we went 1, 2, 3. Now we're going 3, 2, 1. So our next column, fluorine and the halogens, group 7A, is going to be a -1 charge. So we go up the hill, 1, 2, 3, and then at the top of the hill we switch to go downhill, and then it's -3, -2, -1. Then we have our noble gases. And so our noble gases here are 0. Because again, they have 8 valence electrons. They don't want to be gaining or losing electrons. So this is where we get these charges from. Now again, when we're talking about the negatives, we're talking specifically about the nonmetals, right? And so the nonmetals are everything from here on out, right? Those are nonmetals, and then metals are below this line. So the gray is our metals, the purple is our nonmetals. And again, we are not going to be discussing the rare earth metals down here, so don't even worry about them. But you do need to recognize that this is the pattern for these ions. So it goes +1, +2, +3, switch or skip, and then -3, -2, -1, 0. It's very important for you to have these memorized. But again, it's just kind of in a straight line on your periodic table. So let's go back to our notes. So those were our monatomic ions. Now we're going to look at transition metals. So again, these are weird because transition metals can have several different charges to them. But since they're metals, all of their charges are going to be positive, no matter what. Transition metals are always going to be cations. Oops, I don't know what just happened there. Okay, since they are metals, they're always going to be cations. Since they have multiple charges, we always have to be specific about what the charge is whenever we're naming the ion. So for nitrogen, it's always going to be -3, so we just called it nitride. But for a transition metal, it's not always going to be the same number. So for instance, iron, which is Fe, Fe can exist as a 2 positive, or it can exist as a 3 positive. Now, I don't expect you to have this memorized, but if on a test or a homework you're given this ion and you're asked to name it, you should be aware of the proper terminology for naming a transition metal. So we start by just calling it the name of the metal, and then in parentheses, we put the Roman numeral charge. So remember, we have to specify what the charge is, and we use Roman numerals to do that. We already know that it's positive because it's a metal, so we don't have to specify that. So for our first one, that would be called iron, parentheses, 2. And since it's a cation, remember we add cation at the end. And then our next one would be called the iron 3 cation. So just in case you don't remember your Roman numerals, it goes 1, 2, 3, 4 is an I and a V, 5 is a V, and then 6 is V and a line. And we aren't going to be going higher than 6. So just as a reminder. So we have iron 2 and iron 3. Again, we don't have to specify that it's positive because as a metal, it's already assumed to be positive. Then we get to our polyatomic ions. Poly means several or many, and atomic here, right, atom. So many atoms here as opposed to our monatomic, which is just one atom. Now these atoms can be the same element. We see that with peroxide. Peroxide is 2 oxygen atoms. We see that with the mercury 1 ion, since it's 2 mercury atoms. But it's polyatomic because it's multiple atoms, not necessarily multiple elements. And there are lots of different rules associated with the polyatomic ions that we're going to talk about, especially to help you remember them for your polyatomic ion quiz. So let's get to a blank screen and talk about these. First type that we're going to look at are oxyanions. Now you can see the word anion right in there. So these are all going to be negatively charged. And oxy means that they contain oxygen. So these are negatively charged ions containing oxygen. And so for oxyanion rules, we say that the most common ion ends in ate, ate. So for instance, we see the oxyanion with chlorine is ClO3 with a -1 charge. So the most common ion is ClO3 negative. This is called chlorate. If we take away one of those oxygens, it becomes ite, I-T-E. So if we subtract an oxygen, that's now ClO2 with a negative charge. And so this is called chlorite. If we take away another oxygen, so if we subtract an oxygen from the ite, we add the prefix hypo. So if we take away another oxygen, it would be ClO, that's it, right? Just one oxygen with a -1 charge. And so this is called hypochlorite. And then our last thing that we can do here is add an oxygen to the most common ion. And so in this case, we add the prefix per. So if we add an oxygen to chlorate, it'll be ClO4 negative. So this is called perchlorate. Looks like clovate, but that's an R, perchlorate. All right. So as long as you know the common ion, meaning if you memorize on your list of the polyatomic ions all of the eights, you will automatically know the formulas for the ites, the hypos, and the pers. Automatically. Because you know that ite is always one less oxygen than 8. You know that you add a hypo if it's one less oxygen than the ite. You know that you add per if it's one more oxygen than the 8. So if you know one, you automatically know the rest of them. And it makes sense that it's called chlorate, chlorite, right? Because the other element other than oxygen is chlorine. And we keep that first syllable. So we see that with sulfate and sulfite, right? Those have sulfur in them. Phosphate, we see, has phosphorus in it. One other thing I want to point out to you is that even though we're changing the number of oxygens, our charge does not change. So again, if you know the 8, you know the charge of all the rest of them. The only thing that is changing is our number of oxygens here. So those are the rules for oxyanions. Let's see what happens if we add a hydrogen to an oxyanion. Now, H, we said, can either be a cation or an anion, but majority of the time it is going to be a cation. So if hydrogen is an H+1 And we're adding that to an oxyanion. We're going to see that the charge of the new ion becomes one more positive. So in the case of carbonate, carbonate is CO3 with a 2- charge. So if we add an H plus to that, it's going to be HCO3, and then -2 plus a +1 equals -1, which is one more positive than the original oxyanion, right? -1 is one more positive than -2. And so when we're naming these, all we do is add the word hydrogen in front. So this is called hydrogen carbonate. Another common terminology for it when you're adding a hydrogen is to add bi in front. So this is also known as bicarbonate. Whether you know it as hydrogen carbonate or bicarbonate, you are correct. What if we need to add another hydrogen to it? So for instance, with phosphate, this is PO4, 3-. If we add a hydrogen to it, we make HPO4, and remember our charge is going to become one more positive, which is now going to be 2-. This is called hydrogen phosphate or biphosphate. So if we add another hydrogen to it, then now we're going to have H2PO4, and again our charge is going to become one more positive, so now it's a -1 charge. And when we have two hydrogens, we call it dihydrogen. Dihydrogen phosphate. Okay, so before we were looking at changing the number of oxygens but not the charge. Here we're looking at changing the charge but not the number of oxygens. So those are hydrogens with oxyanions. And then just a couple other helpful tips for you as you're memorizing these polyatomic ions for your quiz. You'll notice that there are only 3 ions listed on your sheet that are positively charged. Most of the rest of them are negatively charged. So of those 3, we have ammonium, which is NH4+. We have hydronium, which is H3O+. And we have the mercury 1 ion, which is Hg2, 2+. So you'll notice right off the bat that 2 of the 3 here end in -ium. So anytime you see -ium, you know that it's going to be a positively charged polyatomic ion. And then for mercury 1 ion, it's the only one that we have that is a 2+. Now remember, mercury is a transition metal. So that's why we have to write mercury 1 in parentheses. If you don't write the 1, it's not correct. And again, it's polyatomic because it has 2 atoms. They're the same element, but it's more than 1 atom. So hopefully that will help you a little bit as you're studying for your polyatomic ion quiz. So back to the notes. Now that we understand our ions, we have anions and cations, and we can split it up even more specifically into monatomic ions, transition metal ions, and polyatomic ions. We can start to put these ions together in order to form ionic compounds. Ionic compounds are always going to be made up of cations and anions. So remember, we can't have 2 cations together because the positive charge will repel. We can't have 2 anions together because the negative charge will repel. So we have to have a positive and negative together in order to hold this compound together. Another way to think of it then is that an ionic compound is going to be made up of a metal, since metals are always cations, and a nonmetal, since anions are always nonmetals. Okay, so a binary compound, we know binary, bi means 2, so a binary ionic compound is made up of 2 elements. But the other types of ionic compounds that we can have are made up of polyatomic ions, right? Any kind of ion can create an ionic compound. And these compounds are made up of crystal lattices, which we can see in this picture, where it's pretty much just a bunch of atoms stacked on top of one another. And we can also see that they kind of switch. Every other atom is a different element. So this is called a lattice. These ionic bonds are held together by electrostatic interactions. That's the fancy terminology for it. And all that means is it's held together based on opposite attraction, right? The positive and the negative are attracted to each other. We call that electrostatic interaction. So what's actually happening here in an ionic bond is we are transferring electrons. So remember at the very beginning of this chapter, we said that in order to achieve the octet rule, atoms will either gain, lose, or share electrons. So for ionic compounds, we're seeing the gaining and the losing. In the next chapter, we're going to look at covalent compounds, which is where we see the sharing. So we can see for lithium chloride, for example, lithium, we know, becomes a cation, chlorine becomes an anion, since lithium's the metal and chlorine is the nonmetal. And so that positive and the negative hold each other together. This drawing, with the brackets in particular, is called a Lewis structure. And a Lewis structure is just a representation, it's a drawing of how we show a molecule is bound together. So let me show you how we came up with that Lewis structure for lithium chloride, and then we can do another example. So if we look up lithium on our periodic table, we see that it has 1 valence electron. So we can put our 1 electron wherever we want to, doesn't matter. And then we have chlorine, and we see that it has 7 valence electrons. So we start with 2 paired up together, and then fill in the rest. And there's our 7. So what happens here, we said earlier, lithium has 1 valence. So is it easier to gain 7 or to lose 1? Well, it's going to be much easier to lose 1. And then for chlorine, is it easier to gain 1 or to lose 7? It's easier to gain 1. So we're going to see this transition where the electron from the lithium fills in that last empty space of the chlorine. So lithium lost its electron, so we know it's going to have a positive charge, and anytime we're dealing with something that's charged, we put these brackets around it in a Lewis structure. So lithium now has brackets because it is positively charged, and then our chlorine now has the full octet of its 8 electrons. So since it gained 1 electron, it became negatively charged. And that's where we get the Li and the Cl together. If we look at another example, let's say calcium and chlorine instead. So if we have calcium, we know that it has 2 valence electrons. Chlorine, we said, has 7. This is how we have it drawn in the other side. So one of those electrons from calcium can go over to chlorine, but then we still have that other electron. So our chlorine atom reached its octet, but the calcium ion did not. So in order for it to achieve its octet, we need a whole nother chlorine atom. So that next electron can move over as well. And now everything here, the calcium and the 2 chlorines, have achieved their full octets. So calcium now doesn't have any dots. We put it in brackets, and it lost 2 electrons, so it has a 2 plus charge. Chlorine now has 8 dots. Put it in brackets, it gained 1 electron, so we put a negative, and then we have a second chlorine here. And that's our Lewis structure for CaCl2. So again, this is just drawing a representation of what this kind of looks like in a manner of how our electrons are moving and how we're bonding these atoms together.